but you're not, because L and M, the L by M matrix, because you can have coefficients anywhere in there, it's like as you're shrinking L, you're never, like, in AJK, or not K, but just AJ, the vector, when you make, what you're doing is creating a penalty for non-zero entries of that. So when you make it 0, you're saying the influence of the influence of one of your initial axes is now 0.
Yes.
But if you do it this way, which I may not have explained clearly, but by having the matrix that can have cross components, you're basically transforming everything into another set of axes that can have fewer dimensions, but you're maintaining components of everything, or potentially maintaining components of everything.
Okay. Yeah, maybe we can talk about this after lecture, because I don't really...
Yeah, I don't think I explained it clearly.
Yeah, but if my understanding of what you're talking about is correct, then it doesn't make much difference, because you can collapse all of these rows into a single row by adding all of them, and the result is going to be the same. So if you add a penalization term lambda times L, then you can maintain this part of the objective function by summing up all these rows while reducing L all the way to 1 without changing the first part of the objective function.
Okay.
Which means your optimal is always going to have an L equal to 1. But maybe I'm not understanding your formula correctly.
Okay. Yeah, I'm not. I need to write it out longer. I don't think I explained that correctly.
Okay, so what's wrong with my understanding? I'm just saying if these are all ones, then it's equivalent to summing up all the rows. Right? If your AK are all ones, then AK times CJK is equivalent of, you already said it here, it's equivalent of summing up all the Ks. So if you write down, if you just look at this part, it's actually the same as AJ.
Okay.
Which means you can potentially keep the first part of the objective function to be exactly the same by while reducing L all the way to 1.
Okay.
So you can think about it. So if any part of my understanding is wrong, please tell me after the lecture.
I think your understanding of what I wrote is correct, but I didn't write it correctly.
Oh, okay. You didn't write it. Okay, so let's discuss this afterwards. I feel like it'll take a little bit more time. Any other questions? All right. So that's actually the best practices I want to talk about. I wonder. Okay, so we can either keep discussing your idea, or I can address some of these questions I obtained. The one I think the one I can address today is about optimization. How does Stippis design work, and how to involve the Hessian into the optimization procedure. Which would you rather me to kind of dive into more about the proposed method, or discuss Stippis descent?
Either is fine.
Okay. No preference. All right. Would you be able to describe this a little bit more in a lot?
Give me like 2 minutes to think about it real fast.
Okay, that's fine. I'll first talk a little bit more about Stippis descent.